Yeah, so I'm a compiler engineer at Grok with a Q, and I'm a co-chair with Alex, who's at IBM, and he's currently in Croatia, so good for him. So we're mainly focused with the ONNX MLIR project, and that is a compiler that takes ONNX and translates it into an MLIR dialect. But there's many other open source compilers, including Torch MLIR, TVM, and OpenVNode, to name a few. So normally I just talk about ONNX MLIR, but I also want to show TVM to give an other end of the spectrum. So where ONNX MLIR allows you to do optimizations on ONNX before lowering, TVM is a lot more focused about getting you right into their framework. And that's a very common thing for different hardware providers. You don't really care about the ONNX format, you just want to get into your own intermediate representation. So just to start with ONNX MLIR, I should probably define MLIR because I'll say it probably 40 times, but it stands for multi-level intermediate representation. And it's basically a set of data structures and libraries for defining IRs and doing transformations on different IRs. And yeah, it's gotten pretty wide adoption, and now most compiler engineers, or a large portion of them, are pretty familiar with it. And so ONNX MLIR models ONNX faithfully. The ONNX dialect itself is a vehicle for optimizations and decompositions. We have lowerings from kernel to LLVM, which is our mainline branch that IBM contributed. We also have lowerings to stable HShilo and to TOSA. We also have a few out-of-tree lowerings to custom dialects for people that integrate with ONNX MLIR. And so the main part of ONNX MLIR is that there's a Python script that looks at the ONNX schema, and from that it generates the MLIR op definitions. And then from there, when compiling a model, so at the compiler's runtime, it uses ONNX's C++ APIs for reading the protobuf before using MLIR's C++ APIs for creating the MLIR representation. And so here we can see an example of what the generated code from running that Python script looks like. So the description here comes from the schema that ONNX has. And so this is an example for argmax. So we see the description there. The input types we can see for the arguments. Those are also scraped from the schema, as well as the attributes. And those are set with default values that are, again, scraped from the schema. And so here's an example of what the intermediate representation looks like. You guys are probably can read this pretty well because it looks like what an ONNX textual dump might look like. And then we can do optimizations in ONNX MLIR. And so here we're using declarative rewrite rules, which is like a bespoke language that they have for basically expressing these kind of rewrites. I think Justin showed a way better example with the QKV cache and how you could combine those, but here we have a way more trivial one where we basically spot an unsqueeze and a squeeze and say, oh, if they're doing that on the same axis, well, or axes, we can just get rid of it. And so Apache TVM, in contrast, is Pythonic. So it starts at TVM. So TVM's high-level IR is relax. And relax is defined in C++ with Python bindings. When compiling a model, it uses ONNX's Python API for reading the protobuf, and relax's Python API to create the relax IR. And so the benefits are it's idiomatic Python, it's beginner-friendly, and lowerings look simple, and they look like NumPy routines. So we can take a look at what one of those lowerings looks like. Here we have the hardmax pattern. And so hardmax is basically, it gets the maximum on a specified axis and sets that to 1 and sets everything else to 0. So this can be implemented as in argmax and then a one-hot encoding of that. And so you can see this very much just looks like a simple NumPy implementation, and it's kind of similar to what you might see for a torch to ONNX converter. And so here you kind of have two different ends of the spectrum, right? You have something that like has the full ONNX definition that it represents and does rewrites on, and wants to do analysis in the ONNX world. And then you have the other where it's saying, let's get right out of ONNX and let's go to our own intermediate representation. And so the trade-offs are like, for ONNX MLIR, you're an MLIR. If you're an MLIR engineer, you might really like it. But if you're a beginner, it's kind of hell. So, you know, it takes a lot of onboarding to work with that. And on the other end, you have Python, and that's pretty beginner-friendly. The really nice thing about it is that you can basically do it as an intern. You can write lowerings, so that's super nice. And so you basically get to mix and match what's best for your use case. And I also do want to just say some of the things that we've added to ONNX MLIR. And those are that we now have support for Opset 22, and we continually add more lowerings to those different MLIR dialects. Yeah, thank you.